SwayamPrabha. Digital India. Educated India.
Okay, as I had said, we'll look at a simple propagation through a neural network in this class. So the context is this: we remember that we require a forward model, and all this neural network business is, at least in the first half of my machine learning portion of the course, is in order to approximate a forward model in case we do not have a forward model from the physics. Okay. So for example, we have the parameter m, and if we wish to determine it, but we don't know that the relationship is through the e power m relation, then we try and find out a data-based model, and we'll look at this in greater detail. We'll actually do the fin example the next week. Okay, so you'll see how all the material that we are doing right now is useful. Okay. So either if the forward model is expensive or if it is unavailable, we want data-based models. And the most universal ones are neural networks. Remember, neural networks are simply functions. Okay. As I showed you last time, you can see a neural network as a simple extension of a linear model. Now, actually, there is deeper logic than this. And last year, I had sent several videos explaining this. But what I figured was, in a non-machine learning course, it actually serves more to confuse than enlighten. So we will go with a simple description of a neural network, and in case time permits, towards the end of this module, I will actually give you a little bit more detail about why it is modeled the way it is modeled. But anyway, let's start with the simple thing. This is the analytical expression for a linear model. As you see it, we can call this the sort of algebraic expression. Okay, so the algebraic expression is W0 plus W1x. In case it is a quadratic expression, then it will be W0 plus W1x plus W2x square, etc., etc. We can also write it as Wixi. Some people even write it as W transpose x, and I'll come to this later in this class itself. Okay, and this is the graphical expression here. Take an input node x, output node y, multiplied by W1, multiply 1 by W0, add the two together. Okay, so when I write it as Wixi, notice that I am saying this is sigma Wixi, I equal to 0 to I equal to 1. So this will become W0 x0 plus W1 x1. You will see this notation also in many places. Now, what is x0 here? X0 is simply 1. Okay, this is x0 and this is x1. Okay, so x0 is 1, x1 is x, and this x0 or 1 is often called the bias unit. Now, when we draw neural network diagrams like this, usually the bias unit is implicitly sitting there. Okay, it's usually not shown, but the bias unit is usually sitting there. Okay, so you have to assume that that is there, unless somebody explicitly says that I am not adding a bias. The assumption is there is always a bias unit. In case this is not clear, the example that we will show shortly will make things a little bit clearer. But all I want you to understand through all this is, just like this algebraic expression had a corresponding diagram, if we go in the other direction, this diagram has a corresponding algebraic expression. It is just a little bit complicated, and we used to compactly represent it as a diagram. Okay, but in the end, at the end of the day, it is still an algebraic expression relating this x1, x2, let's call this x3, x4, x5 to some outputs y1, y2, y3, y4. It's simply an analytical expression relating x1 through xy to y1 to y4, and it is fancy or actually compact to represent it as a network diagram or a diagrammatic representation of interlinked nodes or neurons. Okay. So in each neuron, all that is happening is the same as the linear model. This sums up the weighted sum of all these inputs and then runs it through a nonlinear function. So you can write A is equal to G of sigma Wixi. Okay. Once again, this Wixi also implicitly includes one bias. Okay, and there is a weight for that, which we can call W0. Now, how do we notate? Here it is easy to call W0, W1. What sort of notation will we use here? We will see that a little bit later in this lecture. Okay. So the purpose of this lecture is to introduce you to the notation for neural networks, as well as give you a simple handwritten example of how to go from an input to an output in a simple neural network. Okay. So remember this, every neuron has a linear and a non-linear operation. It is simply a composition of functions. Okay. So sigma represents the linear sum and the non-linear sum is represented by G. Typically, in this course, if I do not say what the G is or what the non-linear operation is, it means that you can assume that it's a sigmoid. It's often denoted by this function sigma. Sigma of x or sigma of z is equal to 1 by 1 plus e to the power minus x. Okay. As usual, any questions so far? So the sigmoid function looks like this. I had discussed this in the last class also. So we have this theorem that, yeah, somebody has a question. So we have this universal approximation theorem saying if you have sufficient data in neurons, a neural network, even with a single hidden layer, okay, you just need one hidden layer, but you need to give me freedom to adjust the number of neurons. Then I can approximate any function to any desired accuracy. We had discussed this in the previous class also, that the basic process in which the neural network works is that it is just like an inverse problem, in that typically what will happen is you will set that these are the connections, but you will not know what the weights are which are optimal. Just like here, you will say that fit a line to the curve, but you do not know what W0 and W1 are, and we solve for W0, W1 using a least square process. It's the same thing for a neural network. We set a certain number of neurons and say, okay, what W will fit the given data best? Way to do it is have some data XY pairs, then your neural network for a given choice of W, assume this is something like Liebenberg-Marquardt, it gives you some output, you have a cost function, and by feedback, you keep on improving. And the feedback process usually used in neural networks is a very simple thing called gradient descent, which we'll look at tomorrow. Now, initially, I was planning to do it today. The reason I shifted it to tomorrow was actually I did gradient descent. I did a lot of other background theory last year and then did whatever I'm going to show you right now. Modified it a little bit, but something similar to this I did last year. And I found that most students actually got comfortable with everything only after this detail was discussed. So I actually decided to put it early so that I am assuming it will aid in comprehension. We'll see whether it helps or not. So the idea is to create a neural network, take an arbitrary guess for W. Remember, we are guessing for W and not for X. X is the actual data. W is our parameter, which is what we want to find out. Okay, and then you find out the optimal W by minimizing J. Okay, we'll discuss what backpropagation is day after tomorrow. Okay. So today I'll just give you a walk through a simple neural network. Tomorrow we'll look at gradient descent, the primary sort of optimization algorithm, variants of which are used in all neural networks. Okay. Day after tomorrow we will see this algorithm called backpropagation. And next week we'll deal with inverse problems with ANNs using all these ideas. And then I'll do pins. Okay, so there will be some leakage from back and forth depending on how much time we have in each class. But this is the rough plan for the topics I'm going to cover. Okay. So let's take a simple problem. I'm going to ask you to find out the output of a single neuron. Okay, so let us say this is the neuron and the inputs are 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. If all the weights, assume every single unknown weight here is 1, then what is the output of the shown neuron? So please go to, I'll type this here. Please go here. I'll ask a question, the same question there. And let's see, where am I? So a simple question, and after that I'll ask the same question that I just showed you. Okay, so is everybody able to see it?
I think you have not posted that link, sir.
Okay, I have posted it on the chat. Oh, I think I sent it to Rajesh alone. Sorry. Sorry about that. So there is an input layer and there is an output layer and there are layers in the middle. What are they called? Okay, so just 30 more seconds and then it's a trivial question and then we'll move to the actual question. Okay, I'm finishing the question. So these are not called node layers. The dots that we saw in the middle are called neurons. Typically, these are called hidden layers. Okay, great. I'm going to ask the same question that I just showed you. So assume that every single weight here is 1. Then to 3 decimal places. For example, if your answer is 1.234, please write it as 1.234. If your answer is 0.123, write it as 0.123 rather than 0.123. Okay, so that's the reason why I'm saying this. So please put the first digit explicitly. So D.XYZ. Okay. Please calculate this. Since many people are giving, so what this shows us is that people are getting many different answers. So just a note of caution. Remember, there is the bias unit also, which exists. So I'll give a few minutes for a couple of minutes for people to calculate. Interesting. So just one more minute. Okay, so I can see, let me see, maybe I calculated it wrong. Let's check if looks like nobody got it right. So we have got a lot of variation in the answers. I have done it one way. Let us check if I made a mistake. Here. Okay. So all the weights are equal to 1, which means each one of these is equal to 1. Okay. So we should not forget the bias unit. It's also 1. So the output has two parts. Remember, the first is the linear sum, which is W0, X0. I will call this X0, X1 up till X5. All these added together, 1 plus 0.1, etc., come to 2.5. Okay. The activation after this is the nonlinear part. 1 by 1 plus e to the power minus 2.5. Can somebody calculate it? I got 0.9933, but I might have made a mistake. Can somebody check again?
I think it's 0.924.
924? 0.924 is it? Okay, so the people who got, can somebody check what's one other person? Who was this?
Yes, sir, it's 0.924.
0.924. Okay, thanks. Okay, so let me cut this out. So I might have done entered something wrong in the calculator. 0.924. In that case, the answer that we got there, which was 0.924, was right. Other people got it wrong. So now, since many other people got it wrong, is there any doubt, anything unclear about this now? People did many different things. If somebody else has a doubt, can you please ask? On 0.924, thanks. So I might have done by mistake e to the power minus pi. I think that comes to 0.993. Yeah, I must have entered it wrong. So the people who got it wrong, any comments, questions? Okay. So let me assume that it is clear now if there are no questions. So this is the extremely simple way of actually calculating an output of a neural network. Okay. So let's do this for a slightly more complicated case. This is still not, so typically the terminology used is a deep network. Deep network means if there are 2 or more hidden layers. Okay. So this one still has a single hidden layer. So if you have a single hidden layer, this is called a shallow network. And it was simply branding. So when people had 2 or more, or some people will say 3 or more, it really does not matter. People call it a deep neural network, and it was a genius of branding to call it deep learning. And whereas you see that the calculation is actually extremely straightforward, we could have done it in school in 10th standard, for that matter. Okay. So the question is, if you have a network of this sort, it's a simple network with 2 hidden neurons, 1 input neuron, 1 output neuron, and for the following inputs, okay, for the following weights, find out the output of the given network. X is 0.5. Now I have used the notation. So let me try and explain this notation. Okay. So let us say I have this thing Wijl. Okay, so this is the general notation which I am using here. 2 subscripts, 1 superscript in a bracket. L is referring to the layer. Okay. So layer 1 is the one between the input and the hidden layer. Layer 2 similarly would be the layer between the hidden and the output. And you can imagine as we keep on going further and further, we can add more and more layers. So the superscript L represents the layer. So when I say W011, I know that I am referring to a weight in the first layer, okay, in between the input and the hidden layer. Okay. Now, what does the first subscript represent? Can somebody tell me what it could possibly represent? Oops. Guesses?
Input.
Sorry.
Input index.
Input index. So remember, every weight is between 2 neurons. Okay, we have already established. So if this is the ith neuron of the input layer or the origin layer and jth neuron of the destination, then this is the input, this is the output. Now input and output, I mean it loosely. In this case, it means origin, destination. Okay. So for example, when I say W01, what I mean is I start with the 0th neuron, this one, go to the first neuron of this layer. Remember, there is going to be a 0th bias unit here also. Okay. So 0th neuron here, first neuron here, this weight is 1. Okay. So this one, for example, would be W011. What will I call this? Can somebody tell me?
W02.
W0
02,
zero going to the second one, 2 and 1. Okay. What will we call this one?
W11.
W11 superscript 1. Exactly.
1.
Okay. This
Sorry, it will be W2.
W231.
why 3?
Not 3. W2, either 1 or 0. I don't know.
We will call it 1. Okay. The
Superscript 2.
0 is always restricted to any extra bias unit. There is no bias unit here. Okay. Any genuine neuron will only start with 1, 2, 3, 4. Okay. So it is W21 and superscript
2.
2. Okay. So total, how many unknown weights are there in this neural network? I have listed them all out, so you can actually count them, but You should be able to see it. In the first layer, how many unknown weights? Unknown meaning I have specified them, but how many weights?
Plus 3, two in the first and 3 in the second.
Sorry, I couldn't hear you.
No, it will be 2 plus 3.
It is the first, this thing has 4 unknowns, okay, or 4 weights. See, remember the bias unit, there are 2 here, 2 here, 4 here, 2 here, 1 more. I didn't draw it in order to avoid confusion. So you can see them listed out. W01, W02, W11, W12, all at the first layer. W01, W11, and W21, all in the second layer. So there are 7 weights. Now, like any iterative method, let us say I have given you these 7 weights to start with. And I want to find out for x equal to 0.5, what is the output? I am going to repeat this question on item pool. So please see it there. Oops, sorry. I'll end this question. I'd asked sigmoid of 0.1. Forget that. Okay, here is the question. I have labeled all the weights and I'm asking you the 2 of the intermediate outputs, A11, A21, and y hat, which is the same as A12. Okay, is the question clear? If something is unclear, please ask me. The same this thing, but assume x equal to 0.5. Sorry, I forgot to write that. Oh, I have written it. Assume x equal to 0.5. And for the following distribution of weights, find out the final output as well as the intermediate outputs of the hidden layer.
Sir, can you please begin accepting answers?
Sorry.
So the question isn't showing up. Can you please begin accepting answers?
Oh, sorry. Sorry about that. Thanks for pointing it out.
Can you post the link again, sir? I lost.
Okay. Here, can you see this on the screen? itempool.com/balaji/live.
I'm typing that it is taking to other site, sir, which is asking for it is taking to itempool.com, but not Balaji/live. Can you post that link directly?
Is it working now?
Sir.
Okay. If anyone has any trouble, please let me know. Okay. Couple of more minutes or 1 more minute, then just show the answer and start discussing. Okay. People are still calculating. So just 10 more, 15 more seconds, and then I'll. Oops, I seem to have even I have forgotten to write this here. Several people have got the points 79541 right. I don't know how item pool shows the other two outputs, but let me actually show you a full solution. So here it is, the question that was shown to you. So what we do is simply systematically calculate. For example, the output here is G of, I am going to call this Z1. Okay, so remember this notation. When you have a neuron, I'll use this notation again, and this will get important when we come to back propagation in a couple of classes. So remember, we have the summation portion from all the neurons. Let's call that Z. Okay, so Z is the linear part or the linear sum. Okay, so Z is basically sigma of Wi xi from the input. Okay, and A is the non-linear output. Okay, the non-linear function applied on Z. Sorry, just 1 second. Yeah. So when I say G of Z, Z1 here is W01 x0 plus W11 x, correct? These two are coming here. We add the two together. That's what gives us Z. So if you see, this is 1 times 1. Okay, so W01 was 1 times 1 plus 0.7 times 0.5. 0.7 was this weight. W11 was 0.7 multiplied by 0.5. So G of 1.35, this came to 0.7941. Okay. So before I go to the next one, I mean, once you get this, the rest of it is also straightforward. Did anybody have problem here? Because we got different answers even for this activation. A11, does anybody have a question on just this calculation? Okay, because basically if you can calculate for one neuron, that's more or less what we need for everything for a neural network. Everything else is basically readjustments of the same thing. Anybody have a question on this? I don't know why this is happening. No questions? Okay. Then we can calculate A2 in the same way. Same thing. This would be an output of Z21. I have the same name. A1, A2 corresponds to first neuron, second neuron activation in the first layer. So Z21 is 1 multiplied by this weight plus x multiplied by this weight. Take that, comes to 1.25. Non-linear function over that 0.7773. Okay. I hope everybody else also got the same answer. So I'll just give you a minute. What happened here? To calculate this output now. Okay, since I also didn't reveal the answer because I myself forgot to write it down when creating the question on item pool. So those of you especially who got it wrong, who got A1 and A2 wrong, could you please retry this? A11 was 0.7941. A21 was 0.7773. Under these circumstances, can you find out y hat? Y hat is the same as A12. I'll give you just a minute. Please try and calculate it before I reveal the answer, especially if you got it wrong. I mean, especially if you got A1 and A2 wrong in the previous question. Please try this. Okay. Let me reveal it. So we do the same thing as before. So now this neuron has three inputs, one from the bias, one from A1, one from A2. We do the same thing, summation of Wixi, weight multiplied by the bias, 1 times 1, plus this weight multiplied by the activation, 0.7 times 0.7941, plus this weight multiplied by this activation, which is 0.9 multiplied by 0.7773. So this gives us Z is equal to 2.255, and the activation is now 0.9051, which you get by taking sigmoid of 2.255. Okay, so 0.9051. This is ultimately y hat. Okay. So I have gone through a forward pass of a simple neural network, but it is exactly the same even if you have large. So we can treat the finding of the weights of a neural network as an inverse problem. The forward problem is, given the input and the weights, can you find the output? We just saw we can. But now, given the weights and the output, given the inputs and multiple outputs, we can solve a linear or we can solve a regression problem or a least square problem or a nonlinear least square problem, and then find out the weights. And this is indeed what we'll be doing through gradient descent in the next class, and there are some subtleties there which we will be covering in the class after that. Okay. So just a quick note, in the next couple of minutes, the same problem usually, and I'll be discussing this notation when we come to back propagation because it's easier. Instead of writing it as Z as we just saw, Z1 1 is W011 x0 plus W111 x1. This I can write as W011 W111 multiplied by x0 x1, where x0 is 1 and x1 is x. This lets us write this whole thing as a matrix operation. So we can write something like Z vector of the first layer. So this one would be Z1, similarly Z2 also, which is this. Okay, so Z layer of this layer is Z1 1, Z2 1. Don't get confused by the notation. We will not be using too much of this, but I will have to use it when I finally come to showing you back propagation. This I can write as weight multiplied by input, weight matrix, and this is typically written as W transpose X. Okay. So we have multiple notations. We saw the algebraic notation. Algebraic notation will say sigma wi xi. There is a vector notation, which I am going to skip. Of course, this is the diagrammatic notation, which is simply show the diagram. And finally, there is the matrix notation, which is to write this as W transpose X. Okay. So all these are used interchangeably whenever you read the literature. So just to get you familiar with that, I showed you all these notations. We can do the same thing for the next layer also. For this layer, you will see again it comes as W transpose A now, because A is now the input. Okay. So I can show you a piece of MATLAB code. I can share this later. You can, it's easier to execute in MATLAB if I write it as simple matrix operations. Okay. It's easier to execute it that way. So this is the code for that. This is not of great importance, but I will be using this W transpose X notation in not next class, but the class after the next. I will be showing you this notation also. So that's it. We just did a simple walkthrough through a very, very simple shallow neural network, just so that you have an idea of how it is done. And when we finally come to creating neural networks for bigger problems, etc., this intuition will serve you well. So any questions on this class? Oops, again, this problem. I'll try and erase this. Questions, comments, any doubts that anybody has? Okay. If nobody has any questions, I'll end the class here. Thank you. I'll see you all tomorrow at 10 o'clock. Thank you.